Swayam Prabha. Digital India. Educated India.
The inverse heat transfer. So we'll set the stage for us to study inverse heat transfer. So I'm trying to take a new chart piece. All right. Okay. So I will also, so don't worry too much about this. I'm going to talk about this. So the key drivers for inverse heat transfer are being re-entry vehicle problem. So if you have a re-entry vehicle like this, what is the Q? Okay, what is the Q which cannot be directly measured? So you measure the Q indirectly through the measurements of temperature. You measure Q by indirectly measuring the temperatures at a few places. Okay, forest fires. Okay, if you look at forest fires, the direct measurement of heat flux is gone here. I mean, you cannot just put a heat flux gauge into forest fire, and so you should have some scientific way of getting some infrared thermograms or something and satellite imagery, change in something, change in some brightness, change in some intensity, some other parameter you should, just like the volume of the mercury changes in a mercury in glass thermometer, some funda you have to use. Okay, so detection of forest fire can be eminently done if you use an inverse heat transfer approach. Okay, then cancer detection. This is all new. Okay, for all that, even corona detection is based on the inverse problem, right? The corona, you handle the infrared thermography, some radiation. From the radiation, there is a forward model which says that the radiation is proportional to the temperature. There is a Planck's distribution or Stefan-Boltzmann's law. Then you calibrate it. There is emissivity of the device. All the calibration is going on. You don't understand what is going on inside, but it is there. So even for COVID detection, which is so ubiquitous, everywhere you are seeing that there is some funda of inverse taking place there. The forward model is very simple. Q is equal to epsilon sigma t to the power of 4 minus Q is equal to epsilon sigma t to the power of 4 with just the emission. All right. So forgetting about the background emission and all that. So for cancer detection, you can get the infrared thermogram for the tumorous tissues different from which is having tumor is different from the healthy tissue. This can be worked upon. There's a forward model called the Pennes bioheat transfer equation. Okay, so what we use is called the Pennes equation. That is a forward model. But if you want to become a good scientist in this, you have to set up some experiments and all that. It's very difficult to do that, live tissue and all that. So, or if you want to get raw data, you have to sign up with a cancer hospital or with an oncologist. So, scientist and professor, you can be a stud in heat transfer. You cannot proceed too far. You require the help of doctors, and patients have to sign up and all that. So, it can also be done. What is a funda? Already mammogram, other things are there. Why do you want to do this? Because the infrared thermography is fast and cheap and this thing. So, it can be used as a screening test. The suspect cases can go to MRI, CT scan and all that. That is one possibility. And so this is not necessarily heat transfer, non-destructive testing. Okay, suppose you want to look at the health of an aircraft, you can generate you can send some ultrasonic waves and get the feedback. If there is a crack, the signature will be different. This can also be used for checking cracks in a pipeline and this thing. So there's a lot of process simulation, process control, chemical engineering, the integrity of a reactor, the integrity of a nuclear reactor, all these things you can solve an inverse problem. So based on some, you send some signal, you're receiving the signal. So there is a difference. So there is a forward model. So you send if you send a radar is something which will, so you send some upward electromagnetic wave at 13 gigahertz or 14 gigahertz. If there is no cloud, no rain, nothing will come back. You just wait, nothing is there. Reading is zero. Reading is zero means no rain, but the atmosphere is fully packed with the Nivar cyclone. then you'll get a high reflectivity. So you'll get a beautiful reflectivity signature. Now, during heavy rain, one signature, medium rain, one signature, light rain, one signature, then the rain with ice on the top, temperate region, snow. So all these things as a forward model, remote sensing, radar meteorology. So for atmospheric science too, atmospheric radiation. So these have been key drivers. The original problem solved by Beck was this re-entry problem. Now there are many problems, and you can extend it to many other subjects. Okay, so this is how you, these are the drivers, key drivers for studying a inverse heat transfer or inverse methods in heat transfer. Now, please take down this figure. This is a key. This is one of the most important things. At the end of the course, after 5 years, you forget everything also, it's fine. Just remember this. Just remember this flowchart. So once you remember this flowchart, you can jog your memory and the key ideas will automatically come back. Just like when you go to a chemistry exam, the best, if you're prepared too much, you know that just before the exam, you will feel completely blank. So you'll attain nirvana, you won't remember anything. Okay, this is organic chemistry, terephthalic acid reacts with ethylene glycol and all that. Oh, so many, everything is C6H5OH, all that benzene ring. So you will, but if you're fully prepared, nothing will be, it will be a clean slate. But once you start attending the first 2-mark question, then slowly everything will, you will remember everything one by one if you have studied properly. Similarly, this one, you should have a photographic memory of this flow chart. Once this flow chart is, you are able to recall one by one, you will be able to recall. Now I'll give you 5 minutes. Please copy down this flow chart. All of you, please copy down this flow chart. In between, if somebody wants to ask some question, please shoot questions. Please copy down this flow chart. So this is this R square. So this is the flow chart. Huh? So from here, then I'll explain somebody. All right, go ahead. So I'll wait for a few minutes. If a few people, if you're done, just do a thumbs up. When I see 5 or 6 thumbs up, I know that many other people have also completed. All right. There are a lot of fundas in this. As you copy, try to absorb what is going on. Look at the arrow marks, at the boxes, in the decision box, what is going in and what is coming out of every box.
Sir,
Yeah.
above the forward model, is it written Y sim for simulation subscript for?
Here, forward model.
Sir, above that, is it Y sim, SIM?
Yeah,
for
yes,
simulation?
I am. Yeah.
Okay.
I'm sorry that I have to make it bigger, but why sim? Or you want to make a. Is it okay? It should be Y sim of I. Okay, but that you understand. No? I is the ith quantity. Because I put a Y sim of I. Ith measurement. Varshini, thank you. Varshini has finished. I got Subhash has finished. Anand has finished. Palash Srivastava. Okay, fine. A few people have finished. So very good. As I start talking, you. So somewhere you have to start. Okay, where do we start? That's a good question. We don't start with the forward model. There is a slab. There is a patient. There is an atmosphere. Okay. So there is some activity. You do a measurement. So let's say you have some measurements. Y measured I. Ith measurement. I could be 1, 2, 3, 4. Normally we don't work with one measurement. Several measurements are made. Okay, because you spend time and effort. You try to get the right equipment. You set up the experiment or whatever it is. Okay, or you set up the sample. Even if it's social science, you field experiment, field data. You go and collect data. You do a survey, whatever. So these are all measurements. Okay, that whatever you collect, even if you're doing some survey, whatever data you're collecting is measurements. Y measured I. Y is the measurement. Okay. Now, Why measured I in IHT, in inverse heat transfer, Y measured invariably it is temperatures or heat fluxes. Heat fluxes are a lot more difficult. You need to buy that heat flux gauge and all that. It has some range. You have to paste it. Okay, you have to paste that heat flux gauge on something and calibrate it and all that. It's easier to measure temperatures. Thermometer, infrared thermogrammy, liquid crystal thermometer, platinum thermocouple. So many possibilities are there. So temperature is a physical feel is there. All of we know what is hot, what is cold. We know we can easily get an idea of temperature. It's an easily measurable quantity, and the people can easily comprehend what temperature is. Heat flux is a little more difficult. Okay. So in inverse heat transfer, this is the measurement. So you have a set of measurements. This set of measurements in the parlance or in the terminology of inverse heat transfer, these set of measurements represent the effects. Okay. Now you want to figure out a cost. That cost is coming somewhere in the flow chart, which is not yet clear to us. Now, from these measurements, I want to get the cost. What is causing the MRA of this patient to be different? What is causing the signature from a Boeing 777 aircraft, ultrasonic signature, when I'm trying to test this structural health, is different from a normal plane? These are very ubiquitous, simple, humble, modest, one-dimensional slab is giving some 5 or 6 temperatures. From here to why the emission spectrum from a distant star is like this. So always we are having measurements, we are always having data. Why do people behave like this? So this whole field of consumer economics, consumer behavior, I don't know whether you've read books by Dan Ariely, Ariely, right? He writes books about irrationality, right? The upside of irrationality, why people are irrational. Okay. Or Steve Levitt, Freakonomics. So you must also study something outside of engineering. All right. So lot of data is available. The world is full of data, but we are getting targeted data. So we are clear about what we want to measure. We are also clear about how many measurements. We are also clear about how to do a quantification of the uncertainty or the error associated with the measurement. Because no measurement is perfect. All through your life, you have read that a slab is at a temperature, left side is 100 and right side is 30. So far, you have not even questioned. That 100, how accurate is it 100? You cannot get 100 plus or minus 0. That is there only for exam. That is only there for solving problems and getting a grade or a prize or an award. When you measure a temperature, you are in trouble. 100 plus or minus 100 plus or minus point. If you want to get on with the business of the world, there is always an uncertainty. There is an uncertainty whether internet is working in today's class. Uncertainty whether this Bluetooth will work. Okay. So we have to live with uncertainty. Living with uncertainty, COVID has taught us. Okay. So there is a measurement with an uncertainty, but that uncertainty and all is okay. I can deal with it. I can deal with it. But what I really want to find out is what is the effect? What is the thermal conductivity which is causing that? What is that cancer? How big is the tumor of the patient which is causing that signature? Okay. That is the question I want to answer. But there is no direct this thing. Okay. If the temperature is, if there are 5 temperatures, it is not astrology. If there are 5 temperatures, thermal conductivity is 44. Who will tell you? There is no direct relation. You cannot, it is not available in a book for you to mug up and then say that, okay, if I put 5 temperatures, nobody knows. They'll just give you a set of temperatures. You figure out. I'll give you a set of MRI scan, CT scan. You just figure out. So it is the inverse problem is hard. Because it is hard, because it is meaningful, the outcome is meaningful, it stands to reason that it will be hard. And it stands to reason that it is practical because often we have only data. We have to figure out what are the causes. Okay. Now, how do we approach? Okay, what is this subject? There is a slab. It is giving some measurement. Okay, so it comes in heat transfer. Whether it is coming in conduction, convection, or radiation. Okay, it is coming in conduction. Is it steady or unsteady? Looks like it is steady. Okay, it is 1-dimensional, 2-dimensional, 3-dimensional. Yes, it's 1-dimensional. Is it a cylinder, slab, or a sphere? Plain wall. Is there a heat generation? No, there is no heat generation. Okay, now can I write down the governing equation for this? Yes. Now you are cooking with fire. Okay, there is a forward model. In that forward model, there is a differential equation, two boundary conditions. What are the two on a slab? Left wall, right wall. Left wall, right wall, both the boundary conditions are not there. So if you are based on whatever you have studied in school, you will say that d square t by dx square equal to 0. T is equal to ax plus b. Okay. So t is equal to ax plus b. And at x equal to 0, there is a t1. At x equal to L, there is a t2. Both are not given. So you will either say that the problem cannot be solved. Question is wrong. The question is wrong, so full marks have to be given. That is not the point. Is not to score marks. The point is to find out what is causing the temperature. The temperature is real. This is real world. It is not exam. Now you will say, no, T is equal to AX plus B. Brilliant. So, sir has given 5 temperatures. If you take any 2 temperatures, I can get 2 values of A and B. If there are 6 values, I'll get 6 C2. But the slab has got only one derma. It has to behave. There is only one thermal conductivity is causing it. Out of the 6, which will you choose? This I don't know. You better learn inverse. Okay. But this is where reality strikes us hard. Once there is a forward model, what you will do is, if thermal conductivity is what you want to find out, you will put various values of thermal conductivity in the model, and for that value of x1 to x6, for a simple plain wall, you will generate 6 temperatures. Now you will compare the measured temperature, the simulated temperature. That is the error, because whatever you assume for thermal conductivity is highly unlikely that will be the truth. That will be the actual solution to the problem. Therefore, over and above the fact that the temperature is also in error. So you will take y measured minus y simulated, generally whole square, because the plus and minus error should not cancel. So this you can find out for if there are 10 n measurements. This has to be summed from I equal to 1 to n. So it is a square, the square of the errors. So this is called the least square. I will explain more about this in a later, after some time. So this is called the R squared, or we can also call it as the sum of the residual. We call it as the sum of the residual, or R squared. Very good. Now there is a S. Okay. Now I wrote, is S less than equal to some epsilon? Who will tell epsilon? Nobody will tell you epsilon. You have to decide. Epsilon is the error. How much is this? 10 to the power of minus 3, minus 5. It will not be available in Google. It will not be available anywhere. And it varies from problem to problem. That is why domain knowledge, expertise is required. There is nothing like a universal epsilon which can be used. This is where expertise comes. So you have to decide. If epsilon is 10 to the power of minus 4, how much will the K be off? So you have to study the sensitivity of your. So this is called the stopping condition. What is this? This is called stopping condition. Okay, now to make it very distinct, so we want to be a stud. So we'll make it 10 to the power of minus 6, minus 8, whatever. Okay, let's keep it. Now you get an epsilon first. You put one thermal conductivity. You get a S which is higher than epsilon. Therefore, is the S less than equal to epsilon? No. Okay. By strange stroke of luck, if it is less than epsilon, then you should celebrate. You should go to a cafe. Okay. Yes. Stop. Whatever thermal conductivity. So you are a super stud. You just took one value of thermal conductivity and you got the answer. But it is highly unlikely. But if you get it, celebrate it. Otherwise, it's no. Then you are stuck. How to proceed? Then you have to take another value of thermal conductivity. Who will tell you what value of thermal conductivity you should take? This is the whole game of sampling. What are you sampling? You're sampling the parameter space. What is a parameter space? Parameter space is the set of, is the data vector. It is the vector of parameters which decides the effects. In this case, it's only thermal conductivity K. In a tumor problem, it could be the size of the tumor, the position of the tumor, the radius of the tumor, and how many tumors and all that. It could be the length of the crack, the width of the crack, the number of cracks, if there is a crack in the aircraft or in the submarine, whatever. Therefore, there should be a set of parameters which vary. And all these parameters must be an integral part of the forward model. If you vary these parameters, the temperatures or your y simulated should change. Then who will tell you from, if there are 3 parameters x1, x2, x1, x2, x3, what are the initial values of x1 and x1, x2, x3 you will take? God only knows. from x1, x2, x3, if it comes, if it doesn't convert, what are the new values of x1, x2, x3? We don't know. Therefore, you have to sample. How many times you have to sample? What is an acceptable value epsilon? How do you generate new samples? All these are this comes in the game of computation statistics, inverse, Bayesian method, Monte Carlo method, and all this. Instead of this route, can you directly post this as a minimization problem and take dou s by dou k equal to 0, dou s by dou emissivity equal to 0, and solve it analytically? Yes. This is how they tried initially, and they miserably failed. I don't even remember.
You can take the difference also like that.
Yeah, just jog my memory.
Monte Carlo method, Bayesian methods.
Therefore you have to use some Bayesian. Thank you. Therefore you have to use some Bayesian methods, Monte Carlo methods, statistical sampling. So you have to be good in statistics. Okay, and then maybe if there is a minimization required, this minimization either some algorithm. So you have to be good in minimization. Minimization is an optimization problem. So you have to be good in optimization. You have to be good in statistics. You have to be good in programming. You have to be good in measurements. You have to be good in the subjects. Okay, subject knowledge, measurement knowledge, optimization knowledge, statistical knowledge, programming knowledge in the framework of data. So this also comes under, or you can see whether creatively neural network can be used to solve this problem. Yes, it could be used. What can you do to solve using neural net problem? I should not tell it now itself, then you will lose interest. I will tell it as we go along. So this is a beautiful framework. So this is basically the Siddhant, the philosophy of how we approach. Okay. Why we do so much of hard work is it is not directly possible to invert. Basically because there could be many causes. The effects could be caused by many combinations of causes. And just like the doctor has to find out the right cause for the disease, the heat transfer specialist, the inverse heat transfer specialist has to figure out the right cause for that set of temperatures. Okay, that is one. Okay. Secondly, the simulation has got error. The measurement has also got error, and the measurements and simulations are not infinite, so that you can say that the data will wash away. Data will wash away all the sins. The data will wash away all the sins. What are the sins? The sin is the ill-posedness, because there are because too many causes have to be figured out. If you want to, you kill it. Okay, they are saying, there's a saying in English, no? There are better ways of killing a person than choking him with cream. Okay, okay, like that. You kill the problem. You kill the problem with a lot of data, or you kill the problem with high funda statistical techniques, or you kill the problem with high funda optimization technique. But whatever you do, the problem will be still be low funda if your measurement is not good, or if your forward model is not good. Now, there is this game of data science coming. The data science also, a lot of data is available. This forward model, what these guys are saying is, based on this data itself, can we put a forward model? Then what data? Historical data. Based on historical data, I will completely bypass Professor Newton. Okay, we are all Newton's children, right? So 400 years back, he started all this, and we are after 400 years also, many of his we are all his sishyas. We are all Newton's children. F is equal to ma. This thing F is equal to ma. Little bit you apply it on a fluid, then that fluid satisfies tau equal to mu dou e by dou y. Then you are a CFD. Then I say that Q equal to minus kd by kdt by dx. Q is equal to HA delta T. You are a heat transfer person. Then you stick with tau. Then you are doing solid mechanics. Then you say a Bingham plastic, rheological fluid, all that. You do some fancy materials. You are a material scientist. Then you characterize the materials. You develop new material. Originally, it started out with this. If there is an exception, if something is moving very fast, then forget this. Go to relativistic mechanics. Then it is used in where many things go for a 6, and then here come Einstein, Planck, and all those people. All right. So now, so this is the framework. So as I told you, now it becomes clear to you. You can have any measurement. You can have any forward model. This is valid for any subject where you want to determine cause or causes from the effect. This could be put in economics. It could be put in finance. It could be mathematical finance, stock price, whatever. But the measurement you want to do in that And the forward model you want to do, the forward model may not be equal to d square t by dx squared equal to 0. It may be some other forward model. But there is a forward model in mathematical finance. There is a forward model in microeconomics. There is a forward model in computational biology. There is a forward model in electrical engineering. There is a forward model in architecture. There will be a forward model. There will be a measurement. Always somebody is interested in finding out what the cause is or what the causes are. Therefore, it stands to reason that it will long live inverse, not necessarily inverse heat transfer. So this is because originally in the last century, every field we struggled, okay, to solve forward models. So many subjects came, right? Then you see so many software packages have came. COMSOL, ANSYS Fluent, Star CD, all so many packages, Python, R, all this because some equation has to be solved. Something you want to model. Model is only one part of the story. Alongside these experimentalists, many measurements are available: voltage, current, temperature, heat flux, stress, strain gauge, strain, all that is. Now, marry the measurements and the model in a statistical framework by using some minimization and using some computer programming. Can you get something more than what you would have got if you stuck to only developing a model, or if you're only doing measurements all the time in your lab? Whether this marriage will be successful, we have to see. What are the things? Is it a cure-all? Is it a universal panacea? No. There are some problems which are very, very challenging. That is why the field is still evolving. But one good route will be, as the data becomes better and better, and your modeling we have reached some saturation now. You're comfortable as the data becomes better and better, and we have got command over these two and also the programming. So the kind of problem which you solve using this approach will be incredible. It opens new vistas in our approach to solving problems which are useful to humanity. All right. So that sets the tone. Now let's list the applications of inverse heat transfer. Any doubts in the flowchart? The flowchart is clear enough. So these applications of heat transfer, all that, why talk so much now? Now let's get into let's do problem number 1 of the course. All right. Okay, problem number 1 of the course. I want to give some more theory, but let's not waste more time on this. So this problem we are going to do today and tomorrow. So you have to, because first you note down the data, then I want some ideas from the class. Okay, we'll discuss these ideas, and the mathematics we'll do tomorrow. Problem 1. So it is the simple one-dimensional plane wall. Simple, very simple. So Suraj, I asked Suraj yesterday, we discussed with Suraj, he gave some temperatures which are not okay for Chennai, but that's okay. He gave some temperature like 15, 16, maybe it's okay now. The wall in Jalandhar or somewhere could be like this. Srinagar could be even lower. Okay, please copy down this problem. I will read it once and then I'll give you time. Consider a one-dimensional steady-state conduction. Okay, consider a one-dimensional steady-state conduction. Okay, so consider one-dimensional steady-state heat conduction of the slab. Okay, this is Suraj's words. Okay, consider one-dimensional steady-state heat conduction in a slab. Okay, so it's okay, Suraj. Okay, consider one-dimensional steady-state conduction in a slab. Estimate the heat flux and boundary temperature using least square regression. Least square regression is basically, I have not explained in detail, but you have a good idea. Sigma R squared that we want to minimize. Experimental temperatures at various locations are shown in table 1. The length and thermal conductivity of the slab are 70 mm and 14.4 watt per meter per Kelvin. So please ignore the last line. Also estimate the correlation coefficient. I have not taught you. So leave that or you write it down. We're not going to do this. Now, if you ask me, sir, you bragged about error. I just take it that error is plus or minus. Okay. The error is, so we call it as sigma plus or minus 0.2 degrees centigrade. It won't enter the problem now. It won't enter the problem now. That means if the temperature is 15.46, it could be 15.46 plus or minus 0.2. 14.59 plus or minus 0.2. And the slab X is measured from the left to right. We have got 6 temperatures. Please note, I have not given deliberately at X equal to 0 and X equal to 70 mm. That is the left and right. Then it will become trivial. You will become you will be tempted to use the solution which we studied in basic heat transfer. But please note, even in that case, both the temperatures is also having error, and you're having more temperatures than 2. So you've got a problem of plenty. Therefore, you have to find out one line. There is only one straight line which passes, which cannot pass through all the points, which passes through the points in such a way that sigma of RA squared is minimized. Why that sigma RA squared is minimized? For that I have a lecture. We'll do that sometime next week. Now, if you keep on talking, we will not solve. So the best thing is, the best way to learn, to me, according to me, is learn through examples. So we have straight away started week 2 with an example. Just copy this down. Don't see the solution. Okay. Now let's write the forward model. That's why I have put prerequisite heat transfer, because the examples are going to be for heat transfer. Otherwise, it will just become a statistics course. Okay. So you have to only, otherwise you won't get a feel. Okay. That's why I made it not course on inverse method in heat transfer. You have to apply it somewhere. So d by dx of k dt by dx plus qv equal to 0. Okay. So because it's one dimensional, the net heat conducted in the x direction plus whatever heat is generated equal to 0. But it is clear that there is no heat generation available in the problem. So nothing is given, so we can neglect it. So there is the first assumption, qv equal to 0. Assumptions. T is a function of x alone. K is a constant. All other properties are constant. So this is called a constant property formulation. You can also have a variable property formulation. So once I'm saying that K is a constant, because it is clearly said thermal conductivity of the slab is 14.4. So it is some steel. It is a stainless steel. Okay. Stainless steel is always having around between 13 to 15. Okay. You got various types of stainless steel. SS304, SS316, based on the American classification. So 316 is costlier compared to 304. 304 is very popular. You know, Salem stainless steel. So K is a constant. Therefore, d square T by dx square. So integrating once, dt by dx equal to A. Integrating again, E equal to Ax plus B. So this is the forward model. So we all know this. So temperature goes linearly, and a straight line can pass through only 2 points. There are 6 points. Therefore, there is some gut butt straight away. I am showing the solution. There is a gut butt straight away. So now, so this is as far as the forward model is concerned. So in a typical quiz 1, this is a very simple question. In a typical heat transfer quiz, we will say if left side is at 30 degrees centigrade, right side is at 10 degrees centigrade, what you will do is x equal to 0, t equal to t1. Okay, this is number 5. X equal to L, t equal to t2. So these are called boundary conditions. If there is a problem in which temperature is a function of time, we call it as an IC, initial condition. Okay. Suppose I tell you what the t equal to t1, t equal to t2 was, then you will say that t1 equal to a into 0 plus b. Therefore, b equal to t1. Okay. So t equal to ax plus t1, x equal to L, t equal to t2. Therefore, T2 equal to AL plus T1. A equal to T2 minus T1 by L. Nice. So if you give me what T1 by T2 are there, fine. So 10 out of 10. Quiz 1, I got full marks because I've solved the slab problem. Okay, so this is all very good. But now our problem is different because I have not given T1, I have not given T2. So, but I gave some 6 temperatures in between. So whatever tools and techniques we studied, if I solve differential equation, I know everything. That concept is first shattered. If I know how to solve a PDE or a ODE, I am king. Not enough. That's only one part of the story. You need to know more. If many temperatures are given, you simply don't know how to proceed. Okay, this 10 out of 10 is good. We can get a good grade in heat transfer and we can be happy. Now, if you substitute, now if you substitute P equal to T2 minus T1 into X by L plus T1. Therefore, T minus T1 by T2 minus T1 equal to X by L. Temperature is linear. Is this fine? Is this any good? Is this any good? I will check it. X equal to 0. Right side is 0. T equal to T1. Not bad at all. X equal to L. X by L is equal to 1. T equal to T2. Okay. Is this any good? Yes, it is good. Okay, so far so good. Now, what do we want? What do we want? Q or Q? What is Q? Okay, minus K dt by dx. Minus K into A. Is equal to, it's also equal to dt by dx is 1 by L. So minus K by L. Alas, what a terrible tragedy has befallen man. I neither know T2 nor I know T1. I know only K. I know K, I know L. But I don't know T2 and T1. But I have got Hajar temperatures. There are Hajar temperatures available. Okay. So this forward model is just one part of the problem in real life. So how to get T1, T2 and T1? So instead of trying to get T2 and T1, it is better if I try to get A. After all, A is that whatever T2 by T1 by L or what. Therefore, instead of getting into this route, which because I am a sincere follower of Newton and all that, finally I want a close form. Finally, one solution which will give full marks. I mean, if you are solving an exam paper, I will just disengage myself from this. I will look at this. I want to get A. There is only one A in the value, only one A in the problem. Okay, how do I get that A? Now, since T equal to AX plus B, if I get both A and B, I can substitute any value of X, I can get the temperature anyway, at anywhere. And from that, I can still get T2 minus T1 and be done with it. But now I know that since temperature is linear, if I have two values of X, At two values of x, if you have two values of temperature, I can get a pair, I can get AB. But now I have got 6 temperatures, I've got 6 C2 pairs. Therefore, I need to have a proposal. I need to have a proposal which will go outside the realm of heat transfer. I need to have a proposal to get the best values of A and B. So now, welcome to inverse heat transfer. Is it okay? Yes, we'll do this tomorrow. I hope I've set the stage for this. Any doubts so far? Shall we stop? Can you raise your, can somebody do a thumbs up? Very good. Yes, you have set the stage. We will solve it tomorrow. Chalo, tomorrow, 10 o'clock.
Thank you, sir.
Thank you. I'm ending the meeting. Okay.